The title of the subject is Soil Improvement Techniques. Ground or soil improvement refers to a technique that improves the engineering properties of the soil mass treated. Usually the properties that are modified are shear strength, stiffness and permeability. So three important properties: shear strength, stiffness and permeability. Ground improvement has developed into a sophisticated tool to support foundations for a wide variety of structures. Properly applied, that is, after giving due consideration to the nature of the ground being improved and the type and sensitivity of the structures being built, ground improvement often reduces direct costs and saves time. Need for engineered ground improvement strategies. When a project encounters difficult foundation conditions, possible alternative solutions are: avoid the particular site, design the planned structure flexible or rigid, remove and replace unsuitable soils, attempt to modify existing ground, enable cost-effective foundation design, reduce the effects of contaminated soils, ensure sustainability in construction projects using ground improvement techniques. Ground improvement techniques for different soil types. So we are having different techniques like compaction, dewatering, reinforcement, admixture or grouting. Classification of ground modification techniques: mechanical modification, hydraulic modification, physical and chemical modification, modification by inclusion and confinement, combination of the above. Benefits or objectives of ground improvement techniques: increase of strength, and when we use the term strength it means the shear strength. Reduce distortion under stress, that means increases stress strain modulus. Reduce compressibility, that means volume decreases due to a reduction in air voids or water content under loads. Prevent detrimental physical or chemical changes due to environmental conditions: freezing, thawing, wetting and drying. Reduce susceptibility to liquefaction. Reduce natural variability of borrow material and foundation soils. Trends today: environmental geotechniques and solid waste management using ground improvement techniques, containment and constructive use of waste materials, low-cost technologies with soil with additives, geosynthetics, biotechnical stabilization. So these are the modern trends which are being followed. Catalyst and accelerators. Development of new machinery, particularly for deep compaction. Availability of new construction materials such as geoforms, geocomposites. Emergence of better guidelines for determining the suitability of specific techniques for certain types of soils and site conditions. Better understanding of the geotechnical processes involved and appreciation of the significance of the construction sequence. refinement of methods of analysis and computer modeling techniques. Likely trends tomorrow: microbes to stabilize or remediate soils, nanotechnology to modify the behavior of clay, nanosensors and MEMS. MEMS stands for micro electromechanical system, to characterize and monitor the behavior of geomaterials and geosystems. Remote sensing and non-invasive ground-based sensing technique, and next-generation geologic data models to bridge sensing, computation, and real-time simulation of behavior for adaptive management purposes, and geophysics for urban infrastructure detection. Now we will mainly focus on the mechanical modification, and in today's lecture we are going to focus on the shallow compaction. So mechanical modification can be studied under two headings: shallow compaction and deep compaction. So today we are going to focus on the shallow compaction. So shallow compaction. Compaction should not be a new thing for you. A simple ground improvement technique where the soil is densified through external compactive effort. So water is used to facilitate the compaction process, and ultimately will be having the closer packing of the soil particles. Advantages of compaction: increases shear strength, reduces compressibility, reduces permeability, reduces liquefaction potential, controls swelling and shrinking, prolongs durability. Now, strategies for compaction process are: in the case of constructed fills, specify placement conditions, that means water content, density, depth of layers, etc. Select appropriate equipment, roller, compactor, tamping, and method of operation, number of phase passes, pattern of tamping, etc. Set up adequate control procedures, type and number of tests, statistical evaluation, etc. On this particular slide, you can see the comparison of standard compaction test and the modified compaction test. And these two tests are not the new test for you. And here, laboratory compaction test has been discussed. The standard proctor and the modified proctor at the undergraduate level. You have already studied these tests. Now on this particular slide you can see that operational aspects of shallow compaction, operating frequency, number of passes, and the depth of layers are very important. And here you can see the relationship between number of passes of a roller and the density obtained. So here you can see that different rollers have been considered, and you can see that with the increase of number of passes, the dry density is going to increase in every case. So here you can see the typical compaction curve, and you can see that with the increase of moisture, first the dry density is increasing, and here you are getting the peak value for the dry density, and then with the further increase of moisture the dry density is decreasing. So if you just look at this curve so and just focus on this part, so we can see that here in this region soil grains are densely packed, and we are having good strength and stiffness and obviously low permeability. If you just look at the compaction curve, typical compaction curve, that is like this. So there are three phases that you can consider: the soil, grains, water, and the air. So you can see that in this portion where you are having the best compaction, even some air is present. So you can see this thing that air cannot be removed 100% from the wire through compaction. Here you can see the typical compaction curve and the zero air void curve, or you can say 100% saturation curve, and your actual compaction curve is always on the left side of the zero air void line, and this part where the degree of saturation is greater than 100%, which is impossible, that part is meant for that case. So actually your soil is present in this region where the degree of saturation is less than 100%, and obviously on the zero air void curve we are having 100% saturation. So to draw the 100% saturation curve, we can use this formula. Now the effect of compactive effort can be seen over here, and you can see that increasing compactive effort results in lower optimum water content and higher maximum dry density. So here the compaction energy per unit volume is E1, and here it is E2, which is greater than E1. So you can see that your curve has been shifted to left side and in the upward side. So this thing you can see over here that there is increase in the maximum dry density and decrease in the OMC with the increase in the compactive effort per unit volume. Another important aspect of compaction and clay fabric, you can see higher water content or higher compactive effort gave more dispersed fabric. So if you just look at this compaction curve, and you can see that with the increase of moisture, what is happening, that you are having more dispersed fabric in this direction. And if you just look at this thing, because here more compactive effort energy was involved, so you can see that effect of that increased compactive effort is that there is more dispersed fabric. Well, the line of optimum, if we just join the points, the peaks of that, so this is called as the line of optimum, and usually this line is parallel to the 100% saturation line. Well, on this particular slide you can see the dry density versus moisture content relationship, and you can see that what is happening with the increase of moisture, first dry density is increasing, and after attaining the peak value, then further increase of moisture is causing decrease in the dry density. And you can see that this is the zero air void line, that means corresponding to 100% saturation line, and this is corresponding to 80% degree of saturation. Well, in the literature you would find some relationship or correlations, and by using that you can estimate the dry density, maximum dry density, and the optimum moisture content. For example, in these equations you can see GS, liquid limit, and R number 4. If you are having these things with you, you can estimate maximum dry density, where R number 4 means the percent retained on number 4 save. Similarly, you can see here that the optimum moisture content, it has been related to liquid limit, GS, and R number 4. Here you can see the optimum moisture content, it has been related to log of E and plasticity index, and you can see here the gamma D max, maximum dry unit weight of the soil, is related to L, M, and the optimum moisture content. And here L is equal to this, M is equal to this, and here it is written that the WOPT means the optimum moisture content, PI is the plasticity index, gamma D maximum is the maximum dry unit weight in kilonewton per cubic meter, and E is the compaction energy in kilonewton meter per cubic meter. Okay, now we have read this topic, qualitative studies for compaction theory. There are different researchers who studied the compaction curve in detail. First, look at the Proctor's theory, which came in 1933. Proctor assumes that water has a dual effect on the soil, capillarity and lubrication. It is contended that a thin film of water covers the soil particles due to surface tension. When the films come together, they join the soil particles closer to each other and cause high frictional resistance between soil particles. On the other hand, he stated that sufficient amount of water lubricates soil particles and reduces interparticle forces. Therefore, in relatively dry soils, the dry density is low due to capillarity effect, whereas adding more water reduces shearing strength and increases dry density due to lubrication. Now look at the theory of Hagen-Togler's. Hagen-Togler in 1936 advanced the theory of viscous water to the soil compaction and proposed that the compaction of soil goes through 4 stages of wetting. These stages are hydration, lubrication, swelling, and saturation. The hydration stage involves adsorption of water within the soil particles and formation of thin film on the particle surfaces. The first layer of the absorbed water is highly cohesive, and the high viscosity of water gives the soil a high shearing strength and results in a low dry density. Adding more water to the soil results in absorbed water grading into free water, which is the lubrication stage. When the water layers become thicker, viscosity of the water decreases. Therefore, the shearing strength of the soil decreases too. As a result of decreasing shearing strength in the lubrication stage, the dry density of the soil increases. The maximum amount of lubrication occurs in the OWC. OWC means optimum water content, which is the optimum moisture content. Hagen-Togler asserted that adding more water beyond OWC would result in displacement of soil particles and thus the decrease of the dry density. Through this stage, the soil swells without any change in air volume. During the saturation stage, he stated that all the air is displaced and saturation line joins the zero air void line. Then comes Help's theory in 1956. Help explained the shape of the compaction curve by concepts of pore air pressure and capillarity. The capillary bridges in dry soils resist the compaction pressure and therefore the dry density is low. However, when the water content increases, the menisci flattens and cannot resist the compaction pressure. Hence the dry density increases. When the soil reaches its OWC, the air is trapped and cannot escape. The trapped air builds up high air pressure and therefore reduces the effectiveness of the compaction. Then look at the theory of Lamb. Lamb in 1958 attempted to explain the shape of the compaction curve with the help of surface chemical theories. The electrolyte concentration in the pore water is high at low water content. Therefore, the interparticle repulsion between the soil particles is reduced. The reduced interparticle forces allows flocculation to occur at low water content and results in low dry densities. On the other hand, adding more water to the soil reduces pore water electrolyte concentration and allows double layer to develop. Hence, the soil results in a more dispersed structure. Higher dry density can be obtained as a result of more dispersed structure. Then the Olson theory. Olson 1963 explained the shape of the compaction curve using the effective stress concept. For compaction on the dry side of the OWC, the increase in the water content increases the degree of saturation and results in high pore pressure. Therefore, the effective stress reduces for high water content. As a result of reduced effective stress, the shearing stress of the soil decreases and allows the soil to densify more than for low water content soil. He also stated that the lubrication theory of Proctor and the viscous water theory of Hagen-Togler appear to apply to the low water content moisture density curve. At very low water content, the electrical forces which attract the first layer of the water to the mineral surfaces are stronger than the forces between water molecules. Therefore, the menisci are not formed at this stage and water acts as a lubricant between soil particles. Menisci start to form by adding more water, and this is the peak of the low water content moisture density curve. The compacted dry density starts to reduce again by adding more water due to the development of menisci. Olson concluded that the low water content moisture density curve can be seen only in soils containing high percentage of plate-shaped particles. Then look at the Borden and Sides theory, which came in 1970. Borden and Sides undertook an experimental investigation of the engineering behavior of compacted clay and intended to relate this to the microscopic observations of unsaturated clay structure. Their results indicate that at low water contents, the low dry density is caused by the presence of large air-filled macropores which have high strength and can resist to compaction pressure without much distortion. When the water content of the soil is increased, the air-filled macropores become wetter and weaker. Hence, during compaction, it is easier to distort them and the dry density of the soil increases. If more water above the OWC is added to the soil, the water layer between the soil particles become thicker and the dry density of the soil decreases. So in this way we focused on different theories, and here you are having some sort of summary of those compaction theories. Let's see it. In summary, Proctor capillarity and lubrication theory, Hugging-Togler's viscous water theory, and Lamb physiochemical theory were reasonably consistent with the existing knowledge at the time the theories were developed. However, the advances of knowledge have applied limitation to these theories. Moreover, none of these theories have been subjected to diagnostic laboratory experiments. As a result, these theories are rather speculative. The effective stress explanation of the shape of the compaction curve, which was carried out by Helf, Olson, and Borden and Sides, appear more reasonable than the explanation of the lubrication, the viscous water, and the physiochemical theories. So in conclusion, these works provide predominantly qualitative explanation of the shape of the compaction curve. Further research based on new measurement techniques are needed to explain the shape of the compaction curve and the behavior of the compacted soils. Okay, now here you can see the common compaction curve encountered in practice. So if the shape is like that, so bell shaped. If you are having the shape like this is called as 1.5 peak. And here you can see the double peaks curve is there. And sometimes we have the shape, odd shaped compaction curve. Well, if you just look at that, in the case of pure gravel, you are having the shape of the compaction curve like this. In case of pure sands, we are having the shape of the curve like this. And in case of silt and clay, we are having the shape like that. And this is the zero air void line, which is a theoretical line. So typical compaction curve for cohesionless sands and sandy gravel. So look at that, what is happening? The shape of the curve is like this. So you can see that first with the increase of moisture there is decrease in the dry density, and you can see over here you are having the minimum density, and it is because of the bulking. The low density that is obtained at low water content is due to capillary forces resisting arrangements of the sand grains. And then what is happening with the increase of moisture? There is increase in the density. So this is the typical compaction curve for cohesionless sands and sandy gravel. Now on this particular slide you can see the comparison of soil properties between dry of optimum and wet of optimum compaction. So structure, permeability, compressibility, strength, these are the things which have been considered in detail. Shallow surface compaction, static rollers can be used, smooth steel rollers and pneumatic roller. Pneumatic rollers mean the rubber tied rollers. Sheep foot rollers, where you are having the projections on the drum of the roller. Grid rollers. Impact and vibratory equipment can also be used for the shallow surface compaction. So in this regard, tampers, rammers, plate compactors, vibrating rollers are also available. Impact rollers are also there. So here you can see the vibratory and impact compactors for shallow compaction. So there are different types of rollers, or you can see the compactors available. Now here look at that. If we are going to compact the soil in just one layer, in one lift, so you are having the effect only in the top part of that. But if you have compacted this whole strata in layers, so you can see that you have compacted each layer effectively and you have got the desired density of the soil. This table is showing typical characteristics of impact and vibratory equipment for shallow compaction. So different types of equipments have been considered in this table. Field compaction. Different types of rollers: smooth field roller, vibratory rollers, pneumatic rubber tie roller, and the sheep foot rollers can be used. Here you can see the smooth field roller compacts effectively only to 200 to 300 millimeter, therefore place the soil in shallow layers or lifts. Here you can see the vibratory plates for compacting very small areas, effective for granular soils. And here you can see the sheep foot roller provide kneading action, walk out after compaction, very effective on clays. It would not be wrong to say that sheep foot roller is the best roller for clays. Probably this is a new type of roller at this stage for some of you. That is the impact roller. Look at that. This is the impact roller. It provides deeper 2 to 3 meter compaction, and basically for airfield compaction we use such type of impact roller. Now the compaction control. A systematic exercise where you check at regular intervals whether the compaction was done to the specification. For example, one test per 1000 cubic meter of compacted soil, and as far as the specifications are concerned, minimum dry density and the range of the water content are to be considered. So field measurement of the density can be done by sand cone method or the nuclear density meter. So you can see in the laboratory we can perform the laboratory compaction test, and compaction specifications can be obtained from that, and then we will compact the soil, and after compaction we will determine the field density and the moisture content just to check whether we have attained the desired compaction parameter in the field or not. Properties of compacted soil. Properties of compacted cohesive soil. OMC increases and maximum dry density decreases with increase in plasticity of soil. Empirical relationships connecting the above to liquid limit, plastic limit are available in literature. Properties of compacted cohesionless soil. Maximum dry density is connected to the grain size distribution parameters. Now the properties of compacted cohesionless soil. Compactability and the relative density values are given for different soils, and here you can see in this table typical ranges of densities in cohesionless soils. And the sand properties related to density index are also given. Well, this slide is showing the typical stress strain volume change characteristics for a medium fine sand, and you can see here that in this case the void ratio of the soil is 0.605 and the relative density is 100%, and this one here the void ratio is 0.8, and here you can see the relative density is 20%. So this is the typical behavior. You can see the axial strain along horizontal axis and the deviated stress. So you are having this type of behavior when the relative density is less, and when the relative density is very high, then you are having this type of the shape. And here you can see the axial strain and the volume change in percentage. So this curve is meant for that case where the 100% relative density is there, and this is meant for the case where the relative density is 20. So just this is one example which is given. Approach to specification and quality control in compaction. Specifications and control tests are intended to ensure adequate performance of foundation or embankment of compacted soil according to the chosen design criteria. In order to comply with these objectives, control tests have to be relevant, cost-effective, and representative. Suitability of soils as fills. When high strength and low compressibility are required, but seepage and erodibility are not significant, coarse granular fills are most suitable. As impermeable liner for canals or as core material for dams, clay gravel and poorly graded gravel sand clay mixtures are ranked the highest. Silty soils and dispersive soils, clays, even if compacted well, are vulnerable to erosion by surface runoff or internal seepage. Soils containing organic matter are unsuitable for engineering fills because of their high compressibility under loads and large volume changes due to environmental influences. Common control test. Compaction control tests are essential to check whether the objectives of compaction are achieved or not. It is difficult to check the objectives directly, and properties, strength and compressibility are assessed indirectly. Control tests in terms of water content, density, penetration, resistance are conducted. So compaction control procedures. Laboratory tests are conducted on samples of the proposed borrow material to define the properties required for design. After the earth structure is designed, the compaction specifications are written. Field compaction control tests are specified, and the results of these become the standard for controlling the project. These specifications are expected to ensure an expected level of performance in terms of shear strength, compressibility, permeability, which are related to bearing capacity, settlement and drainage and seepage, etc. Now the types of specification. This is very important slide. End product specification and method specification. So first look at the end product specification. This specification is used for most highways and building foundations as long as the contractor is able to obtain the specified relative compaction. How he obtains it does not matter, nor does the equipment he uses. So generally, end product specifications are used for highways and the building foundations. Then comes the method specification, which are the detailed specification. The type and the weight of roller, the number of passes of that roller, as well as the lift thickness are specified. A maximum allowable size of material may also be specified. It is typically used for large compaction projects, not for ordinary projects. Then look at the relative compaction. This is the formula for the relative compaction, and in fact the relative compaction is the dry density that you have obtained in the field divided by the maximum dry density that you obtain in the laboratory multiplied by 100. Relative compaction can be related to relative density in this formula like this, and keep this in the mind that relative compaction that can be used for all types of soils, but relative density d sub r, it is meant for granular soils only. Determine the relative compaction in the field where and when. First, the test site is selected. It should be representative or typical of the compacted lift and borrow material. Typical specification call for a new field test for every 1000 to 2000 square meter or so, or when the borrow material changes significantly. It is also advisable to make the field test at least one or two compacted lifts below the already compacted ground surface, especially when the sheep foot rollers are used or in granular soils. Experience and engineering judgment suggests the approximate minimum number of the field density and moisture content test as follows. So embankment, impermeable liner, subgrade, base coats, and backfill. Methods which can be used in the field. Destructive methods are core cutting method, sand replacement method, volumetric method, rubber balloon method, Proctor method. And as far as the non-destructive methods are concerned, nuclear gauge method and the impact tester. So in destructive method, core cutter method, which is mainly used for the clays, and the sand replacement method, which is also called as the sand cone method, that is applicable to a variety of soils, are being used extensively in the field. Now in these slides you would find some details about the destructive methods, and you have already studied these methods at the undergraduate level, so you can go through these slides. Here you can see the core cutter method and the sand replacement method. Here volumetric method and the rubber balloon methods have been discussed briefly. Okay, difficulties with destructive methods. The measuring error is mainly from the determination of the volume of the excavated material. For example, for the sand cone method, the vibration from nearby working equipment will increase the density of the sand in the hole, which will give a larger hole volume and a lower field density. If the compacted fill is gravel or contains large gravel particles, any kind of unevenness in the walls of the hole causes a significant error in the balloon method. If the soil is coarse sand or gravel, none of the liquid method works well, unless the hole is very large and a polythene sheet is used to contain the water or oil. Now come to non-destructive methods. Principles. Density. The gamma radiation is scattered by the soil particles and the amount of scatter is proportional to the total density of the material. The gamma radiation is typically provided by the radium or radioactive isotope of cesium. Water content. The water content can be determined based on the neutron scatter by hydrogen atoms. Typical neutron sources are americium, beryllium isotopes. So here you can see non-destructive methods of three types. This is the direct transmission method, backscatter method, and the air gap method, where you are having the gap between this base of the instrument and the surface. So radio isotopes are used to find moisture content and density of the soil. It is useful for large number of tests, and the results can be obtained in a few minutes time compared to 16 to 24 hours, which you need in the oven drying method. So radium or radioactive isotope of cesium is used to emit gamma radiation. This radiation gets scattered when it passes through the soil and is proportional to the density of the soil. A counter measures the scatter of gamma rays, and with the constant source, it depends on the absorption capacity of the soil. A calibration plot helps in considering the count of density of soils. So field density method, which it can be related to the nuclear density meter, and in this way we can prepare a calibration chart. So calibration against a compacted material of known density is necessary, and for instruments operating on the surface, the presence of an uncontrolled air gap can significantly affect the measurements of the nuclear density meter. Now the compaction trials. For projects where large quantities greater than 20,000 cubic meter of relatively homogeneous borrowed materials have to be handled, compaction trials may be used to determine the most effective compaction methods. In particular, these trials indicate the following: the most efficient compaction equipment, the type and depth effect of the densification, the minimum number of passes needed to obtain the required density. Well, this is the last slide for this shallow compaction. Mechanical compaction of soil is an efficient way of ensuring good engineering behavior. For shallow compaction, control still advanced methods using sensor technology are being developed in the field. So that's all about the shallow compaction. Thank you.